Hi, I'm George Musser. I'm a contributing editor at Scientific American magazine, and author of The Complete Idiot's Guide to String Theory, and I'm here to answer your questions. Okay, the first question is, let's say I'm an alien on a ship 65 million or more light years away. Using a telescope, I look at Earth and I see dinosaurs living their daily lives. If my ship started traveling towards Earth near the speed of light, would I see the dinosaurs moving faster, fast-forwarded? Well, it's a great question, a subtle question. It's the kind of thing that comes up a lot when you deal with relativity theory, Einstein's theory of relativity. And I actually asked a physicist to make sure I would get the right answer for this. So the bottom line is the dinosaurs are going to be moving a lot faster as you see them on the ship. And the reasoning goes something like this. When you set out, you're seeing the dinosaurs 65 million years ago. When you arrive, you're moving at something like the speed of light. You see them 65 million years in the future. So 130 million years have passed in all, according to the dinosaurs' time. Things look a little different on your ship. On the ship, the distance seems to be somewhat shortened by the fact that you're moving so close to the speed of light. If you're moving at 99% of the speed of light, the distance looks something like only 10 million light years. So you need 10 million years to cross that distance. Okay, 130 million years have passed on Earth, 10 million years have passed on your ship. The dinosaurs seem sped up by a factor of 13. They're moving and they're stomping around and chomping on prey 13 times faster from your view on the ship than they are to themselves. Okay, so question number 2, another great question. If all movement is relative, how can there be a speed limit? In order to measure speed, you have to measure it against something. So what is the speed limit measured against? So it's really a great question because it gets at the heart of relativity theory, Einstein's theory of relativity, and what does that theory mean and the weird predictions that it makes. The bottom line is the speed of light is the same for everybody. It doesn't matter what you're measuring it against. You can measure it against a spaceship, train, car, boat, walking down the street, standing still, whatever, and you will see the same speed of light for everybody. And that's completely different from other things that we observe in nature. If I'm traveling in a car and I throw a ball off the car, I have to add or subtract the speed of the car to the speed of that ball. But that's not true with light. If I shine a flashlight off that car, it will be moving at the speed of light relative to me on the car, and the speed of light relative to someone walking down the sidewalk, speed of light relative to someone in orbit looking on, alien on a distant planet. Everyone will see the same speed of light for that light beam that I shine off the car. And that's a weird fact, that the speed of light is the same for everybody, but it underlies everything that you've ever heard about with Einstein's theory. It underlies the fact that time ticks differently for different observers. Lengths look different to different observers. The space and time themselves are combined into something called space-time. You can't really treat space and time independently. They're united in this thing called space-time. And it's all a consequence of this fact about the speed of light being the same for everybody. The third question goes in a somewhat different direction, but I really like it as well. If a black hole's event horizon gets bigger every time its density gets bigger, i.e. it absorbs mass, why hasn't the whole universe collapsed into an enormous black hole yet? Shouldn't this kind of expanding black hole be getting bigger exponentially? And will this be the end of our universe and possibly the birth of a new one, or where ours began a big bang? Well, it's a very perceptive question because it's true. As black holes take material in, they get bigger. So you think that there's an exponential growth to them, that as they take more stuff in, they get bigger, they're a bigger target, they suck more stuff in, they get bigger and bigger and bigger at an exponential rate. And it's true, black holes do grow at an exponential rate if you keep feeding stuff into them, if there's material for them to eat. In fact, there's something in astrophysics called the salpeter time, which is something like a few tens of millions of years. And that shows how fast they will double in size. They'll keep doubling and doubling and doubling in size every few tens of millions of years if stuff is being fed into them. Now that if is a big if. Although black holes are monsters and they're vacuum cleaners and they're sucking everything in, they're still pretty small on a galactic scale. So they're not a huge target. They're sitting at the center of a galaxy in this case typically, and it's hard for them to get enough material to feed on. So they tend to choke off basically their own growth. Not just because it's hard to feed stuff in, but because the black hole is actively changing its environment. It's spraying stuff out into space and actually pushing stuff back out. It's heating stuff up, preventing it from falling in, so they regulate their own growth. So it's very hard for them to grow. Continued growing at an exponential rate. They probably did initially, but then they kind of level out. And they achieve something like a few tenths of a percent of the mass of their overall galaxy. They have kind of a self-regulatory mechanism. Well, thanks for the great questions. If you have other questions for the next expert, please leave them in the comments below. And challenge the next expert. Give them hard questions like you gave me.